All right, welcome everybody for day 2 of the Chicago Roadshow. This is the FinTech track, so if you like money, you're in the right place. So we're kicking things off today with a presentation on Cassandra and Rocks TV by Yekasa and Randy. So let's welcome them to Chicago for the Roadshow. Kick things off.
Hey guys, how you doing?
Good. Hey.
Awesome. It's a beautiful day in Chicago today. It's talking to my wife. My daughter goes to school here, and she's like, "This is the day that this is like worked out so perfect." Anyway, my name is Yekasa. I am the head of database engineering at State Street. State Street Bank is a bank. It's a custodian bank. So for those of you in the financial track, you guys understand what that is. We move 10% of world's transactions. So that's about 36 trillion. Given the asset value of the market keeps going up and down, we have no idea why. Maybe it's the tweet that's making all the difference, right? One tweet sends it this way, another tweet sends it that way. Who cares, right? So they're a bank. All right. So one quick disclaimer. Everything that I'm going to say here is my own. Does not reflect State Street opinion, and there's a lot more language in there. Take it, read it at your leisure. All right, so let's talk about the actual challenge that we are trying to solve, right? So State Street, like most of the other companies, adopted the microservices architecture for greater developer productivity, right? Makes sense. And as we look at this landscape, by the way, let me first introduce myself and introduce Randy. I kind of completely bypassed that step. I'm Yekasa, and I'm joined by Randy Abernethy from RSM. Randy and his team are the experts in Kubernetes and cloud native. So we've leaned on them quite a bit to implement some of the solutions that we are going to talk about here, right? So when we look at across this microservices architecture, the one thing that stood out was this key value storage. Well, this is nothing new, right? So this has been around for 10 plus years, whatever. So we looked at, I was tasked to develop and deploy a key value store as part of the DBaaS. So DBaaS, we always look at 3 important things for deploying anything under DBaaS umbrella. First one is open source. Well, why should it be open source? Well, because in the financial track, right, we can develop the compliance, the audit controls, all of those things, good things that we need to satisfy the financial industry, deep into the stack, and all microservices can benefit from it. If it's open source, it makes it a lot easier for us. We can go right inside the stack and kind of build it once and deploy for everybody. High performance. So this is my favorite, which is a high-performance system is any system that delivers a lot of throughput, like a million QPS with a modest cluster. And then latencies that are really low, like sub-millisecond latencies. A lot of the times, people look at the mean, median, and the averages, which is okay, which is important. You got to look at that. That is necessary, but it's not sufficient if you're going to deploy this at scale. You have to really focus on the P99s. The tail latencies are going to come and get you. Those are the ones that will wake you up in the middle of the night when the system is having timeouts. When you have to pick up the phone, and that's what you're going to, at least understand where your P99s are. And Randy is going to talk us through the experiments we've done and the data we've collected and show you some very good performance samples. The next one is the cloud native, right? So this is where the Amazon, the Googles, everyone is, teaching us these days is being cloud native. And, so there's not a consistent definition. I tried to Google this around to see if there's a consistent definition. There isn't a consistent definition, but at least in the cloud native space, what it means is you containerize your deployments, and then you automate as much as you can, right? That's the simplest way I could put it. So what do you automate? Well, pretty much everything that you can, right? If you're managing scalability, managing availability, managing recoverability, backup and restore shouldn't be a thing that we do manually, right? It should be, systems should be doing these things automatically. And if you haven't tested your backup, guess what? That backup is no good. right? We've run into so many instances where you go to the backup to restore something and the backup is no good for whatever reason, right? So you have to come up with a system that's continuously backing up, continuously restoring, right? So you take a backup, you test it, and then when it is good, you put it in the archive. Otherwise, you don't even put it in the archive because who knows if it's going to work or not. Anyway, so these are the three pillars that we were looking at before we took a solution on board. Okay, so welcome to Cassandra. So Cassandra is, we looked at different key value pattern stores out there. And of course, Cassandra always floats to the top. It's given its maturity, its stability, its reliability. But what really made it compelling for us was the work that the RocksDB engine or the Instagram guys have done, which is they've replaced the lowest layers of the Cassandra stack with RocksDB. RocksDB is from Facebook. It's a key value store. It's just a library. It's you hook it up and call it however, use it however you want. And Cassandra guys have, or the Instagram guys have taken the Cassandra, preserved the top half, and replaced the bottom half. Why? Because the RocksDB is implemented in C code base, and it performs a lot more efficiently. And you'll see the difference in P99, which is the one that I was talking about. So Cassandra is Cassandra plus RocksDB. By the way, Decon from Facebook has given a wonderful talk last year at Cortana Live. If you haven't seen his slides, I would encourage you to go take a read. And then, of course, now that you have Cassandra, how do you deploy this, right? So that's the next big question. So we looked at Kubernetes. As you all know, this is another open source from Google, and what it gives you is the container orchestration, and fully loaded with all the features that you would need for production scale deployments, like stateful sets and replica sets and persistent volumes. At least that's good enough for us to go to production. So that's our solution, right? So you have Cassandra, you have RocksDB laid on top of Kubernetes. That's the solution. Okay, but that solution does have gaps. For example, if you download Cassandra today from the Facebook repo, it doesn't think if you have snapshots working, right? So the list snapshots, when the time comes to either take a backup or recover, you need that functionality. Repair tools, some of the repair tools aren't working. The streaming isn't working properly. There's many gaps here. So what we've done is we've actually built a backup and restore solution, which Randy is going to walk us through. It's a pretty elegant solution, and we are taking it to the next level. But this is phase one, certainly. It's not in the open source yet. If you guys are interested, do let me know, and we may be able to do something for you before we put it all out in the open source. By the way, State Street is going all Kubernetes and all open source, so you'll see a lot of buzz from State Street going forward. My team has contributors to RocksDB, so we actually work very closely with Facebook in making those contributions as well. All right, let's talk about the orchestration. So now that we have some of the backups and restore and things like that taken care of, you still have to package up your application and deploy it in a way that you don't want all replicas to be on one side of the AZ, because if the AZ goes, then you lost your copies, your availability for that range of the key states. So you want to be careful. So there is a little bit of work there in terms of orchestration, right? So, and then of course, Kubernetes gives you those bells and whistles. And then when it comes to the containerization, Cassandra, at least the developers that were using Cassandra, they fell in love with the environment variables. You can actually add some environment variables, and Cassandra will pick it up at runtime. We lost all those things when we containerized this. So what we did was we had to add that back in, so to make it usable for our developers at State Street. So there's more gaps to fill, but what we've done so far with the monitoring, backup and restore, and all that, now we feel that this is good enough to deploy this system. And what you're going to see now in terms of the implementation, Randy is going to walk us through. You'll see not only how the backup and restore has been implemented, monitoring and all the other good stuff to make it production ready, but also you'll see some performance numbers from a production-like cluster. With that said, let me invite up Randy. Take it away.
Thank you. Thanks. All right, so I'm going to talk about the implementation, and I usually talk about enough that probably don't need to fight, but the implementation is really kind of driven by the things that Yekasa was highlighting, the fact that we wanted to move to cloud native, so that means microservices and container packaging and dynamic orchestration. But one of the things that cloud native, at least at the very early stages, didn't really address was platform services. Anything that's stateful sort of is anathema in a microservice sort of world where you're supposed to be building these little stateless guys that you can scale to the nines, right? And they're elastic, you start up 10, you shut down 5, that's not the kind of slapping around you want to do with something that's storing your data, right? Moving a terabyte around, every time you scale is probably not a good idea. So it's a completely different approach that you take for stateful types of systems in a cloud-native environment. And usually those solutions are part of the platform. They get consumed as a service by the application developers. So the devs that are in the cloud, are going to use DynamoDB or what have you that the cloud provider is offering, and they just consume it as a service. But when you're deploying this in a financial services institution, there's still a lot of regulations and things like that keep you from potentially doing some things in a public cloud environment. And so a lot of these firms want to have all the stateful stuff running in their own environment. So Kubernetes along the road came up with this thing called the stateful set, and then more services and features started to show up. And so Yekasa's team is basically charged with creating this platform from nothing. And again, the tool for the job seemed to be Cassandra for a part of this. They actually have several different database platforms that the developers get to choose, right? Most devs want to be able to say, hey, this is a relational task. I'm doing transactions and stuff. Give me an RDBMS. Great, we got that. They offer that as a service. And then, hey, I need something that's crazy scalable and ridiculously fast. That's what this piece was for. And so on the back end, you have this well-known, tried and true code path that's really rich and powerful and has lots of features and is really, really fast and linearly scalable largely. But this whole thing is Java, right? And everybody knows that the Achilles heel in Java is garbage collection. When the GC kicks in, it's stop the world, and if you're in the middle of a financial transaction, that's not cool. So when you switch over to Rocks, you're now dealing with C++ engine, there's no garbage collection, you have a much more deterministic kind of latency all the way out there at P99. And so the beauty of this model is that you get both. You can do application stuff that doesn't have this maybe time-sensitive criticality and can handle a little blip every once in a while over here, and you can get the rich functionality of being able to do queries that produce lots of records and things like that. This is a key value store. You give it a key, it'll give you a value. If you say, give me all of the things that are like this, it's going to barf, right? It's not going to help you. So not every application can use this. Not every application can use this. But between the two of them, you get this massive scale, and you get to choose kind of your latency profile based on feature set, and it really kind of works out nicely. So the idea then is to package this up into a container and just be able to have as many of these as you need to. And to get to that 1 million query per second, you need about 10 pretty beefy boxes, 10 pretty beefy cloud instances. We'll look at the spec coming up. But the platform basically looks like this in a Kubernetes environment. We basically have a bunch of computers, and we get those guys provisioned with NVMe's. So these are really fast SSDs in the cloud instances, and they're locally attached, right? So we're not going over a network to talk to a storage array. And the reason that people like to go over networks to talk to storage arrays is because they can click a button and snapshot them, right? If you're in AWS or what have you. They can do things like click a button and back them up. They can do things like detach them from one system and attach them to another system. You can't do that with these. They're on the box. But the beauty of Cassandra is Cassandra lets you create key spaces with X replication. And if you want 2 copies of your data because you're a little paranoid, or 3 copies of your data because you're really paranoid, you can do it. And when a box goes down, you just don't care. Cassandra's going to take care of data distribution in the background. Now you need the developers don't care. Yekasa's team cares because they got to make sure there's enough headroom for that data replication to take place when those kinds of failures happen. But beyond that, you're not going to lose anything, right, at this level. So this is in the Kubernetes world, this would be called a persistent volume. And there's a local volume manager that we've got set up that provisions all of the SSDs that appear on an instance automatically. And that's set up as a daemon set. Kubernetes, a daemon set, carries a service that runs once on every single node. So if you want to expand your cluster, just add 4 nodes, and then boop, instantly the provisioner is going to pop up on that guy because it's in a daemon set. It's going to automatically create PVs for all of the disks that are there, and then automatically you're going to be able to use them. The next piece is up at this level. There's a scheduler in Kubernetes that knows how to find a home for a stateful set. Yekasa mentioned this. AZs are really important, right? Cassandra replication has to know about your availability zones, right? It's got to be wired into your fault domains, because if it doesn't know that these 3 machines are in the same AZ, it could put all of the replicas of your data in that same AZ. And when the AZ goes down, bye-bye data. So we've got all of this kind of configured so that the scheduler, you know, this guy is learning from Amazon using a thing called a snitch, where the AZs are. And so it's going to make sure that replicas of your data are distributed across AZs. So anybody who's got 2 replicas or more is going to have at least 2 AZs involved. If you have 3 AZs and you have triple replication, you'll have 1 in each AZ. So the stateful sets are going to be scaled across AZs, and the data is going to be scaled across AZs, because the awareness is not only at the Kubernetes level in the stateful set and the Kubernetes scheduler, but also up there at the Cassandra level. So on the observability front, observability in cloud-native systems is really critical, because you take these monolithic things that you used to have before, here's my app, and you explode them into hundreds, maybe tens, hundreds of little services all talking to each other. And when something goes wrong, what the heck happened, right? Is it that service, this one? Was it a network issue? Did a node go down and it was just transient, right? How do you know? Well, observability has got 3 legs. There's logging, which are events, right? A customer connected, that type of thing. There's metrics, CPU, memory. That's a time series, right? Every 5 minutes, show me CPU memory. And then there's tracing, which is context-sensitive information, right? This user made this call, which caused that service to talk to that service, to talk to this service, to hit this data set, to come back, right? That's context-sensitive stuff, tracing. So we need to have all of that stuff baked into this solution. And so the first piece of the puzzle was to get the metrics so that we could actually monitor the state of the systems and things like that. Fortunately, Cassandra's got all sorts of great JMX output that you can use to, you know, see transactions and latency and things like that. And so all of the Cassandra pods are instrumented for this JMX data. But what we want is for this to be database as a service, right? The idea is that developers say, I need a Cassandra cluster. It's going to need this capacity. Stand up the boxes and let me use it. And I want to monitor it, right? So probably the most popular tool in the Kubernetes space for monitoring is Prometheus. And so a Grafana dashboard wired up to a Prometheus instance lets you watch your own cluster or your set of clusters if you've created more than one. And the trick is that if you've got a Kubernetes cluster that has 20 different developers operating on it, all with separate applications in different namespaces, you can't have 20 different Prometheus instances scraping all of this data. You have to have a single instance that's part of the platform that collects all of the data, and then in a federated way, this guy actually provides the data out. Now, there are some ways that you can do things differently, but this is pretty much the best model with the lowest utilization of the actual underlying system. So we've got a master instance, which is really just a time series database with a scraper, and then we've got the instances that are created per DBaaS. And so when you deploy one of these Cassandra instances, you get your own dashboard, and we've set it up with best practices, counters, and meters, and of course you can customize it. So the solution deploys the stateful set, which we mentioned, configurable size, you can make it however big you want, and it optionally deploys the monitoring solution we just talked about, also an HPA. So a horizontal pod autoscaler. In cloud-native systems, you get faster by adding more. And the downside is that a lot of databases don't work that way, but Cassandra does, so it's perfect for this solution. And you can set this horizontal pod autoscaler, and it will watch storage, So if you start running out of storage, it'll provision new boxes because you're using local storage. There's no way to get more, right, except adding boxes. It will also watch CPU memory, and it'll scale on custom events if you want to that come out of Prometheus, like transactions per second or something. So that can be turned on, automatically scales. And we've also set it up to be one way. Normally, horizontal pod autoscalers go both ways. They're elastic. But you don't want to scale down your database without human supervision, right? That's a really bad idea because all of a sudden, not only did you just take away a machine, which means everybody else gets the load of that box shared across them, but also that data just disappeared, which means every one of those replicas, those partition replicas, have to show up somewhere else. And now all of a sudden, data is going to be copied, and when you shut that guy down, it's going to try to push all of its data through the network. And so not only is the load going to come up because that guy disappeared, but the load is going to come up even more because there's all this operational overhead that has to happen. And you could collapse your whole entire environment in production setting. So we made that so that it only goes up. It can never scale you down, it can only scale you up. So humans can choose to scale down if they want to, but that's up to them and their monitoring, savvy. There's a backup scheduler also that you can deploy, which will automatically snapshot the entire cluster and then push it out to an S3 compatible object store, which could be Swift on OpenStack or it could be Minio or something like that. And all of this stuff, by the way, is using Helm, which is a way to create sort of a YAML template of an application. And then the users just fill in the little things that they want to change, like turn this on, turn that on, and give me 8 nodes, right? They fill in some variables, they hit the button, off it goes, and you get the whole solution. So resilience in AZ diversity is kind of interesting because not only do you need to have nodes distributed across multiple availability zones, but you also need to have your pods for this stateful set that actually is housing the Cassandra solution distributed across the availability zones. And the Cassandra engines running inside those pods have to know what availability zones they're in so they can distribute their data. So it's really like every tier of this solution needs to know what the fault domains are. And so it's pretty straightforward from a Kubernetes standpoint in a cloud. Azure, AWS, Google Cloud, they're all going to make it very easy for a Kubernetes solution to figure out, hey, this node is in this AZ, and to spin up nodes in the appropriate AZs. We use a solution called COPS, which is Kubernetes operations, and it's pretty easy to use on Amazon, probably the easiest. But there's things like KubeSpray out there and other tools that you can use to deploy on clouds that work great. And there's also a lot of Kubernetes as a service out there. All the big clouds have it, IBM, Google, Amazon, Azure. Click a button, get a 12-node Kubernetes cluster or a 1,200-node Kubernetes cluster, whatever you like. And so that's kind of at the lowest level, pretty much squared away. When it comes to the pods, that's not automatic. The scheduler is going to say, hey, you want another storage pod? Let me find a node that has the requirements that you asked for. And if you're saying, I need this much CPU, this much memory, and I need to have, it has to have the storage label because it's a special node that has the right NVMEs on it, then the scheduler will just find one of those. It doesn't particularly care about what AZ that particular pod lands in unless you tell it to. And so, there's a little bit of Kubernetes artistry in the solution where you have to, in your specifications for how to set up the stateful set, say I want anti-affinity by availability zone. And so what happens is the first pod goes in some random AZ, the next one goes in some different random AZ because it's got anti-affinity. And let's say you only have 2 AZs, the third pod now, it doesn't really matter which one it picks, right? They're both equally, unhappy, right? If you're over here, you have another pod with you. If you're over here, you have another pod with you. So it just picks one. But once that happens, now it's clear. Hey, there's much more gravity over here. I'd like to stay away anti-affinity from the 2-node AZ, and I'm going to go over to the 1-node AZ. And so it just kind of keeps ping-ponging. Or if you have 3 or 4 AZs, they'll do the same thing. And so that's at the Kubernetes level. And then at the Cassandra level, there's a piece of Java code called a snitch. And you can configure different snitches. Some of them you can say, here's a file that tells you where I am. So in the old days, when everybody was running this stuff in their own data centers, which many people still do, of course, the rack was the failure domain, right? Because the rack has a top of rack switch and power, and so if that switch or that power goes down, the whole rack goes out. So you'd rather have your Cassandra cluster distributed across 3, 4, 5 racks. So in Cassandra, failure domain is a rack. So we have to have some way of figuring out in a cloud-native environment how to figure out from OpenStack or from Amazon or from Google Cloud or whatever it is, what the AZ is, and translate that into Cassandra's rack, nomenclature. And so that's what a snitch does. It can do it from a property file where you just set it up, manually, but that's not, really cloud native. You want to automate everything, or you can use a pre-built snitch. So we're actually using the EC2 snitch, which conveniently works on OpenStack, and it also works on EC2 on Amazon. That's what it was built for, of course. The downside is that if you ever wanted to deploy this solution on bare metal Kubernetes, where there's no cloud, but there's still fault domains, right? Kubernetes has a special label that you put on nodes, beta.kubernetes.io/failure domain/zone, and then you set it to something that it can provide anybody who asks. And so future work, one of the several things that we would like to do going forward to make the solution even better is build a Kubernetes-specific snitch. So at the moment, you either have to manually snitch or you have to do something that's EC2 compatible like OpenStack. But that's how we get the Cassandra side to know, where to put the data. Is that failure domain connection between the cloud to the Kubernetes layer all the way up into Cassandra, because that's where it matters. All right, so yeah. Autoscaling. So the autoscaling, I mentioned this is kind of a one-way solution. So this is a combination of something built into Kubernetes called cAdvisor. cAdvisor is a container advisor. You can run it on Docker, just standalone, and it'll spit out all sorts of great metrics on what's happening on that Docker instance. But it's built into the Kubernetes node manager, the kubelet these days. And so that thing's spitting out metrics like how many pods are here, what the total committed memory and CPU is, and things like that. And then you can get other stuff like I/O and tricky advanced stuff from the Prometheus scraper. And all of these metrics go into Kubernetes through this aggregation API. So you have the custom metrics, you have the metric server metrics, and conveniently, the horizontal pod autoscaler has access to all that. So anything in a Kubernetes cluster you can measure, you can use to trigger a scaling event. And so historically, memory and CPU have been the things, but for us, that's not the most important thing. If you're about to run out of disk space, that's really important. It doesn't matter if CPU is quiescent. If you're about to run out of disk space, you've got to scale, right? So, so we have our HBA wired up to a bunch of really important, kind of metrics, and it will then automatically scale up. Now, the way that HBAs are set up on Kubernetes is there's a min and a max, right? You can never scale beyond the max, and you can never scale below the min. And so we've written a little bit of glue in each one of these pods so that every time there's a scaling event, they move up the minimum to the number of pods there are in that stateful set. So it'll never, ever be able to scale down. And so you can respect the developer's request for never charge me more than X by saying I've got 10 nodes, I don't want to have more. But you can also make sure that you never end up scaling them down and causing their rapid collapse in production. So backup and restore. So this is a tricky one. Backing up a machine is one thing. Backing up data in an eventually consistent cluster is another thing, right? There's no way, it's a physics impossibility to know the distributed state of a distributed system at any moment in time, because you don't know which things are in flight, which things are committed, and the two generals problem, right? Hey, there's these two generals and there's a battlefield here and the bad guy's here. The bad guy has 5 armies, you've got 3, and this other guy's got 3, right? If you both attack at the same time, you win, 6 against 5. So send a message to this guy saying, hey, let's attack. This guy says, he sent me the message, let's attack at midnight, but if I attack and he doesn't know I got the message and he doesn't attack, I get wiped out 5 against 3. So I'm gonna send a confirmation. Hey, I got your message. This guy's like, okay, cool, they got our message. But they don't know that we got the confirmation, right? What if they're gonna wait until we tell them that we actually got this? So we send them the confirmation, right? And this is a battlefield. The courier might get shot, right? It's a network, right? You don't trust it. And so you just can never know, right? And so how do we deal with a situation like that? Well, Cassandra is really good at handling this, and it has the ability to know, which commits happened after which other ones. There's a leader in the process and things like that. So all we really need to do is evoke a snapshot, a freeze at a given point in time across every node that's fairly close timestamp-wise, right? And then we need to push all that data out to some sort of storage system. So what we've done is we've created a little backup script that is essentially going to be invoked by a Kubernetes cron job. So you can set up a cron job and set your schedule, how often you want a snapshot. Every 5 minutes, if it's maybe really critical data, or every half an hour, or once a day, whatever you like. And that script in parallel is going to hit every single node at the exact same moment and say snapshot. Now the problem is, if you snapshot all the nodes at once and have them all start loading to a object store, you're going to crush your network. And so part of the puzzle is this delay here, which is going to be applied incrementally based on the stateful set's ordinal. So if you're node 0 in the stateful set, you go right away. If you're node 1, you multiply that number by 1, and that's how many seconds you wait before you start uploading. Again, that could be more sophisticated. It could actually monitor activity on the S3 store or whatever and say, hey, wait till these guys are actually done before you start uploading. There's other things you can do. But this is kind of a nice happy medium. It's a simple solution, easy to monitor. And so when the cluster backs up, remember this is DBaaS, so we don't know how many of these clusters there are. There could be 50 of them or something. And so you specify your object store, right? In this case, s3amazon.com. You specify the bucket that you want to go to, so rocks back. You specify the name of the cluster. You actually don't. That's going to come automatically from the cluster. When you create one of these in the Helm chart, you give it a name or it's going to generate one for you. So this is Cassandra 01. That's the specific cluster. There could be 50 of them. Then you have your availability zone. Aha! If you back up a node, and there's 2 copies of this data, and that's the guy from availability zone B, you don't want to restore it to availability zone A. You're back in this nasty boat where if A goes down, you lose all your data, right? You have to know what the AZ is that you're backing up. And then finally, you've got the node ID in Cassandra. That's like a GUID, right? And then we just put the data in there. Now, the tricky thing is, you can't copy the whole data set of a multi-terabyte storage engine on a regular basis. It's going to be too expensive. So what you really want to do is you want to just copy the diff. And the beautiful thing about Cassandra and ROCs is that they both are capable, when you snapshot them, they're going to create SST type files, right? They're going to create these static files that never change. Now, these files can go out of date, right? They can become old. There's lots of tombstones in them where deletions have been flagged, but the data's still there. And then you compact that every once in a while, right? So compaction is another big expense that you got to watch out for in these databases. But the beauty is that those SSTs, once created, will never change. So when you get a snapshot where the memory's flushed, you got your SST files, you can know that those things can be safely backed up because they can't be appended. They can't be, changed. And so the nice thing about this solution is it knows which SSTs it's already uploaded, and it only uploads the new ones. And so each snapshot has a bunch of hard links to the actual real files in the table directory, but you can tell from the table directory which ones you've already got. You just create the new ones. So it's essentially an incremental backup solution that is pretty efficient. So on the recovery side, this was an interesting one. So imagine node 1 goes down, and it's not coming back. What you need to do is you need to be able to say, okay, I want to bring this guy back, and I want it to recover in the proper way. So all you actually need to do in this solution is you need to create a recovery file. So you go into the S3 storage system, you create a recovery file that specifies which node you want to restore, and that's it. And then when you create a new node, and you can do this by scaling the stateful set, or you can do this by deleting the PV of the guy that failed so that he has to get recreated somewhere else in the cluster. Either way, when the new guy starts up, there's a special container in our Kubernetes pod called the init container that's going to go look to see if there's a restore job. So the first thing he does is he looks on his disk and says, is there data there? No. Okay. Either I'm a brand new node just adding more capacity, or I'm supposed to be recovering for somebody. So then he goes here and he says, is there a recovery job? Yes, there is. Great. Downloads all that data, and then when the data is local, it kicks off Cassandra like nothing ever happened. He rejoins the cluster. He's got a new IP, but that just takes 30 seconds or so to negotiate with everybody else. Hey, I changed my IP, sorry, but I'm back, and everything's good to go. So that's kind of the recovery side of it. So tweaks, we mentioned the snitch, that's future work. Also, there's a custom seed provider. When a Cassandra cluster starts up, or like if you added a new node, how does it know which cluster it's supposed to join? There could be 40 of them out there. So there's got to be some way of telling that guy, hey, these guys are like the keystone nodes. These are the special nodes that are never going to change. And in the stateful set, when you scale it up, nodes have an ordinal that never changes. The IP could change when they move around, but the ordinal never changes. Cassandra 01-0 is always Cassandra 01-0. That's its identity. This data is associated with that thing, right? And so 0, 1, 2, 3, 4, 5, 6 scaling up. When you scale down, it goes the opposite way, 6, 5, 4. So the most stable elements of a stateful set in Kubernetes are 0, 1, 2, and 3. And so we've got a custom seed provider that talks to the Kubernetes talk, figures out exactly which of these guys are the stateful set 0, 1, 2, 3 of the current set, and it provides that to Cassandra, and that's how the nodes join the cluster. So again, it's this subtle but very lightweight glue between the Kubernetes piece of the platform and the Cassandra piece of the platform. So a little bit on performance. In testing this solution with the Roxandra backend, only 10, kind of surprising, like 10 nodes, 10 instances, i3.8 extra larges, which have 32 cores, 244 gigs of memory, and 4 NVMe disks, will give you 1 million reads per second. That's pretty good for 10 nodes, right? 100,000 reads per second, scaling linearly up to 1 million with 10 nodes. And Yekasa and I were talking at lunch, actually. One of the experiments we still have on the plate to do is these are big nodes, and they're, from bang for the buck, they're more expensive than like a 16-core box. And Cassandra actually really likes to run on smaller boxes because every box you create has more I/O, right? There's more concurrency, more parallelism, less bottlenecks and bus, contention and things like that. And since it's such a great, scale-out solution, we want to kind of see if we took this and turned it into 8-core or 16-core boxes, which would be cheaper bang for buck, CPU-wise on Amazon, and then we doubled or quadrupled the number of boxes, would we get the same performance or would we get more, right? So my supposition is that only a hypothesis. I haven't tried it yet, but we're going to work on this. 20% less money or 10% less money, at Amazon, and maybe 10 or 15% better performance because you've got more I/O. In the scale out, and that's one of the big bottlenecks, memory and I/O. So we'll see. But at the end of the day, you heard Yekasa talking about how important that P99 is, right? You got 1 million clients. 1% of them is 10,000 people. 10,000 people are going to experience this, right? P99 latency. So you're over here saying, oh yeah, my average latency is 2 milliseconds in this big 1.5 terabyte environment. That's great. Yet it's not, because a full 10,000 of those million people or those million transactions are getting hit with 12 milliseconds of latency. And in the P999 case, where they smack into a garbage collection, you're in a really bad way, right? 263 milliseconds, that's a quarter of a second. That's a pretty serious experience hit over 2. And when you look at the switch to Roxandra, right, using a key value store, sure, you don't have all the features, but if you just need that functionality, why pay for all the extra? And you're in this mode where you have a much more predictable, kind of P99. So that's that. So the solution is a bunch of artifacts. There's the COPS deployment. There's the metrics solution. There's the Helm chart that deploys all the stuff. There's the seed provider. Soon there'll be a snitch. There's the container builds. There's the backup and restore scripts solution. And Yekasa can speak to this, but the idea, I think, is to open source pretty much the whole solution as a thing you could use at some point. And yeah, so we got like 1 minute or something?
Yes.
Okay, but yeah, so at this point then, any questions? Yeah?
How are you great implementation?
So how are we going to open source it? We haven't exactly figured out exactly how we're going to open source it. The idea is we're working with Facebook. Some of these codes, the Roxandra changes that we are making are directly migrating back to the Facebook repo. So if you download Roxandra from Facebook repo, you have all our changes. Roxandra changes, we're working with Instagram. Again, restore is not something that they have in the Cassandra. I mean, they have snapshots, but backup and rest of the kind of solution that we built doesn't fit there. So we're trying to figure out how best to push that out. We haven't exactly figured that out, but you guys are interested in the backup and rest of the note, I'll let you know when it's available. The help charts, yes, all of that will be open source. But again, Cassandra is not necessarily containerizing, right? So it's so we will put that out separately, maybe under the next academy. I don't know. We have to figure that out. Yeah, all the help charts and everything that we built here will be open source. Snitch is actually we thought it would be it's super cool because you can now understand the hardware, variable, Kubernetes deployments, as well as Amazon EC2 instances. So it's got the whole thing.
Azure,
Yeah.
GCP. Yeah.
You can customize it to any environment, so that's the cool thing about it. Really open source that too as well. There's a lot of good stuff here.
Actually, I have a question about this snitch there. Every time that I've tried to build something similar to that, I get into the trouble of like what happens when that gets out of sync. Like what happens with the
Labels?
either labels or if it's stable enough to use labels or whatever state it is that it's holding, it's out of sync with reality.
Yeah.
How does snitch?
So you have to make sure that the labels are managed very carefully. So if you open up the cluster administration to everybody, then it becomes out of control and we see. So what we do is we provision the hardware and we provision these labels. We are super careful. So that's one way to kind of manage. Because this system is not, I mean, you can build a set of discoveries if you want, right? Where, the hardware is registering all its labels and the snitch is kind of, discovering the labels on the fly and adjusting the externality, but that's a much bigger task for something that's simple as, to build distributed records.
Question for reads. The dirty reads, are you keeping all the replicas? Like consistent reads?
Yeah, they're random read. In that example, they're random reads with just a key. So it's a key lookup of a row, and it's random keys being tested. It's Cassandra stress.
It's a good, Cassandra stress, so that's what it was run. But consistency is at the API. You can configure the problems.
So ROS doesn't affect that.
Yeah.
What does it actually affect?
ROS is basically at the lowest level. It's the library read and write as much as it can to do this. To the layers of hierarchy.
So we can't only use ROS to get something.
Yeah.
Am I using any features or just
So some of the features we've listed, the predicate, you can have a select star from each page. We always have a predicate. That was one limitation. So it's just saying select star.
The where, it has to be, there has to be a key in the where clause,
Yeah, which is actually a good practice if you ask me, because it's a key value store. I think the access pattern should always be based on a key. We shouldn't be doing a select star. Whoever invented that or opened that up in Cassandra, I'm actually against that.
Yeah, full table scan's not good in a database like that. But as far as, it's kind of an interesting thing is that the Cassandra layer in this is the clustering smarts, right? So when you do a query and it hits one of the Cassandra nodes, any of them, right, because there's no master, they're going to say, okay, which partition is that in? And where is that partition? And then they send the query to that guy, or if it's all of them, then they all get the query and they produce the results and the coordinator then organizes the data. So these are the simplest of queries, right? It's like, here's a key, okay, the coordinator says it's in that partition, give me the data. That guy goes and grabs that, uses a Bloom filter or whatever down at the lowest layer to get the data out of the disk where it's in memory, and then returns it back and the coordinator sends it out. So you'd expect these operations to be fast, but that's why you're getting like, with this solution, you're getting crazy scale, like 1 million queries a second. Pretty good.
Can you briefly explain how the switching between ROCs and Cassandra works? So I get what the reason it's there to skip the garbage collection, but how is the garbage collection taken out of play in the queries when using ROCs? Maybe I'm missing out.
So it's still there on all the Cassandra side of the fence.
Sure.
But because the Cassandra stuff is a lot a lot of it's pre-provisioned, and so once all the caches and everything get warmed up, there's not a lot of activity there.
Sure.
But basically, it's a J&I request from the Cassandra engine down to the storage engine. And so the Instagram guys went into Cassandra, which wasn't really designed to be pluggable storage-wise, but it's not unprecedented, right? MySQL allows InnoDB and ISAM and all these different plugins. And so they just took that same methodology and came to Cassandra and said, what's the stuff that's cluster smarts about figuring out who to talk to? And what's the stuff that's disk smarts about how to be a smart disk cache? Let's draw the line there. And then they basically created an API, and then they took that same thing, because when you call Cassandra and it's getting ready to hit the storage engine, the key space is what matters. That's the discriminator. And if the key space is RocksDB, you're going to find it to be something else, but if it's RocksDB, then the decision logic they added into Cassandra will call the Rocks engine. If it's some other key space, it'll call the Cassandra engine. So it just JNIs into RocksDB, and then after that, you're automatically in C++.
So just to summarize, you've basically taken a lot of the volatility out of the database side by leaving kind of the connection and
the stuff that's changing, right? Inserts and all that. Yeah.
And rocks. The
That's
stuff
right.
that's stable is in Cassandra.
If you think about, so if you're reading and writing these objects, there's a lot of, especially when on the right side of things, the update side, you're doing a lot of compaction. You guys have used HBase. HBase was notorious for IO chunks, right? You would go into a compaction cycle, and then guess what? It doesn't matter. You want to respond to the users. That's all because of the IO chunks and compaction going on inside the HBase. RocksDB guys, kind of figured, so that they looked at that and they kind of did all that compaction work in RocksDB, in the C code, which is not very efficient. So it takes away a whole bunch of, there is still Java, to your point, but it is, the use of Java is minimized because most of the heavy work is being done by the C. Makes sense. Thank you.
Cool. Thanks, everybody. Oh, I'm next, okay.
Sure. Are you guys going to distribute these slides or?
Yeah, we can tweet them out if you want to provide me with the link. I can get them out to the folks that are following along. So just so everybody knows, we have about 10 minutes to be in transit to the next talk. We'll be starting up here again at